We have dealt with many situations in which fluids are static, but we know that one main characteristic that fluids differ from solids is that fluids flow. In the case shown in this picture, there are smokes rising up from the fire and water swimming from a fire hose. There are also the flow of air and the flow of water on the ground. Fluid dynamics allows us to know more about the physics of fluids in motion. Flow rate Q is defined to be the volume of fluid V passing by some location through an area during a period of time t. As shown in this picture, we have the volume of fluid V equals to A times the length d, where d is related to the so-called average velocity of the fluid. The SI unit of flow rate is cubic meter per second. Flow rate and velocity are related, but quite different. Flow rate not only depends on the average velocity of the fluid, but also depends on the size of the fluid, or more specifically, the cross-section A. This picture shows an incompressible fluid flowing along a pipe of decreasing radius. Because the fluid is incompressible, the same amount of fluid must flow past any point in the tube in a given amount of time to ensure continuity of flow. That is, the flow rate must be the same at point 1 and point 2. And that is A1 average V1 equals to A2 average V2. This is called the equation of continuity and is valid for any incompressible fluid, usually liquids but not gases. In this particular case, because the cross-section area of pipe decreases, the velocity must necessarily increase. Generally, speed increases when cross-sectional area decreases, and speed decreases when cross-sectional area increases. For a system with many branches, continuity of flow is maintained, but it is the sum of the flow rates in each of the branches in any portion along the tube that is maintained. Then the equation of continuity has a more general form, N1 A1 V1 equals to N2 A2 V2, where N1 and N2 are the number of branches in each of the section along the tube. Let's look at this example together. In part A, we can use the relation between flow and velocity to get the average speed of the blood. We have Q equals to 5.0 liter per minute, which is 8.33 times 10 to the minus 5 cubic meter per second, and A equals to pi r squared, which is 3.14 times 10 to the minus 4 square meter. So that the average velocity equals Q over A, and we get 0.27 meter per second. In part B, since blood also flows through smaller blood vessels known as capillaries, and there are many of them, so that we can rearrange the equation N1 V1 A1 equals to N2 A2 V2, and we get N2 equals to N1 A1 V1 over A2 V2, and we have 5.0 times 10 to the 9 capillaries. We have learned that when a fluid flows into a narrow channel, its speed increases. That means that its kinetic energy, half mv squared, also increases. But where does that change in kinetic energy come from? This increase in kinetic energy is related to the net work done on the fluid to push it into the channel. It is found that there is a pressure difference when the channel narrows. This pressure difference results in a net force on the fluid, and the net work done increases the fluid's kinetic energy. As a result, the pressure will drop in a rapidly moving fluid, whether or not the fluid is confined to a tube. I have found this picture online to better illustrate what happens when a fluid flows. If we consider the same volume of fluid first moves at a velocity of v1 when the cross-section area is a1, then moves at the speed of v2 when the cross-section area is a2. If in a general case, there is a change in height so that the potential energy is also included. According to the conservation of energy, we have the force due to pressure, P1, that is F1 times the distance S1, which is related to the velocity, plus kinetic energy plus potential energy at the position 1 equals to the work due to P2 plus kinetic energy plus potential energy. And that is P1A1, which is the force 1, times V1 delta T, which is the distance S1, plus half rho A, that is rho A times V1 delta T. This whole thing is the mass of the fluid at this point times V1 squared plus rho A V1 delta T, again the mass, times GH1 equals to everything at position 2. Since the fluid is incompressible, we have A1 V1 equals to A2 V2. Or we can say that we are considering the same volume of fluid, so that the A1 V1 delta T, the volume, equals to A2 V2 delta T. So that we can cancel all the factors of A1 V1 delta T or A2 V2 delta T, and we get P1, the first term, plus half rho, the middle is cancelled, V1 squared plus rho, middle is cancelled, GH1. And the right hand side is P2 plus half rho V2 squared plus rho GH2. So that the whole thing, P plus half rho V squared plus rho GH, is a constant. And this is the general form of Bernoulli's equation. This general form of Bernoulli's equation has a few specific situations. When the fluid is static, we have V1 equals to V2 equals to 0, so that the Bernoulli's equation becomes P1 plus rho GH1 equals to P2 plus rho GH2. That is P2 equals to P1 plus rho GH1 minus H2. This means in static fluids, pressure increases with depth. Since h is the height, the deeper we go into the water, the smaller H2 is, and the bigger the pressure P2. If we set P1 to be 0 at the surface of the water, this equation becomes the familiar relation P equals to rho Hg, where h is the depth of the water. On the other hand, when the fluid it's moving, but its depth is constant, h1 equals to h2, so that the Bernoulli's equation becomes P1 plus half rho v squared equals to P2 plus half rho v2 squared. This situation is so important that this equation of the fluid moving at a constant depth is often called Bernoulli's principle. We can see from Bernoulli's principle that pressure drops as speed increases in a moving fluid. For example, if V2 is greater than V1 in the equation, then P2 must be less than P1.